Good morning guys, welcome to today's worked exam answer video, which today is me tackling 4 different AQA GCSE paper 1 questions. So I'm going to do a titration calculation, I'm going to have a think about completing an ionic equation for a displacement reaction, and then explaining why the reaction is both oxidation and reduction, so a redox reaction. I've also got an explain why the reactivity of the halogens decreases going down the group question. And then I've got a reaction profile diagram, which instead of you having to draw, it's been drawn for us, but there are mistakes. So we've got a C3 question, a C4 question, C1, and then C5. I'm going to try to do all of these in one video, so obviously if there's bits of it you want to see and other bits you don't, just, obviously feel free to skip forward and just watch the questions that you would like to. But I know I don't do nowhere near as many GCSE questions, so if you're a GCSE student watching this, hopefully these sorts of questions will be useful. But please let me know if you would like more videos, and if so, on what. So for question number 1, we're doing a calculation involving an acid, citric acid, and an alkali, sodium hydroxide. So this will have been done via a titration, and we are going to do the calculation side of things to work out the concentration of sodium hydroxide solution in moles per decimeter cubed. So me personally, I like to use 2 colours for the information pertaining to the alkali, which in this case is sodium hydroxide. Goal is to calculate the concentration of that. And then we've got citric acid, we know a volume and we know a concentration of that, and there's its formula in our equation there. From there, what I tend to do with all calculations, and this applies to A-level students as well, is I will always sort of write out the equation and then use the formulae for the relevant substances as like my column headers. So I'm going to make sure obviously I leave myself enough space to do that. And this is only really going to be important for the reactants because we're only dealing with the sodium hydroxide and the citric acid. So at that point I can leave less space. And in terms of the rows of the sort of table I'm constructing, it doesn't matter, I don't think in this case, whether we have concentration above volume or volume above concentration. I'm going to do it as concentration as the top row, and then volume as the next row. And then you're always going to want to be calculating moles because that's how we can compare things in chemistry. And then I'm also going to need the ratio from the balanced chemical equation. So we can fill that in first, it doesn't have to be first, but by ratio we're looking at the balancing numbers in the question, so, or in the equation, sorry. So we are going to need 3 times as many moles of sodium hydroxide to react with the citric acid. So the ratio is 3:1. Now the other thing that we can do is copy down from the question the information that we have for the sodium hydroxide and the citric acid. Now the volumes here have been given in centimetres cubed, sorry, but they need to be in decimeters cubed. So it's up to you whether you want to write them in the table as centimetres cubed initially, and then convert them underneath into decimeters cubed, which we would do by dividing by 1000. Or just write them into the table straight away in decimeters cubed. There's no right or wrong way to do that, so long as they're in there in decimeters cubed, because that's the value we're going to need. Concentration of the citric acid I can also copy in, and I know that that's a concentration because of the units, moles per decimeter cubed, so the number of moles in a set volume, which ultimately is our concentration. So that can go in there. And then the other piece of information we've got is the volume for the sodium hydroxide. And again, it's up to you if you want to write it in to the table in centimetres cubed first, so long as you know you need to convert it into decimetres cubed to use in your calculations. Now from there, what I would hope that we can then see is, if this is what we're wanting to find out, we've got enough information to work out the moles of the citric acid. We can then use the ratio to get the moles of the sodium hydroxide, and we can then use our moles and volume to work out concentration. So in terms of the calculations we're going to need moles is equal to concentration times volume in order to get the moles of the citric acid. So we're going to do 0.05 times the volume in decimeters cubed, and that's going to give me 6.65 times 10 to the minus 4 moles. Then we can use the 1:3 ratio to say, if that's how many moles of citric acid we have and we need 3 times more sodium hydroxide, the moles of sodium hydroxide would then be multiplied, those moles, multiplied by 3. So 1.995 times 10 to the minus 3 moles. And then in order to work out the concentration, we're going to need the rearranged form of this equation. So concentration is equal to moles over volume. So then for the sodium hydroxide, I can take the moles, 1.995 times 10 to the minus 3, and divide that by the volume in decimeters cubed, 0.025. And that gives me a concentration of 0.0798. And that would be in moles per decimeter cubed. And hopefully you can see how I've done that. You don't have to set it out in a table so long as you do the following 3 things. 1, get the moles for the substance you can. 2, use the ratio to get the moles of the other substance. 3, find out the missing value. In this case, it was a concentration. It might be a volume. As always, any questions about the first part of this, let me know. Okay. Moving on to question number 2. Magnesium displaces zinc from a zinc sulfate solution. So I guess the first thing that we need to be, happy with here is the idea of displacement. So in displacement, a more reactive metal in this case can displace a less reactive metal from a solution of its compound. So magnesium has to be more reactive than zinc for the displacement to work. If we had it set up the other way, it wouldn't work. Zinc would not be able to displace magnesium from magnesium sulfate. Then it says complete the ionic equation for the reaction, and we should include state symbols. Now, what you might find helpful to do initially, and you might not, it completely depends. You might find writing out the full chemical equation first is helpful. So if magnesium, solid, reacts with zinc sulfate, ZnSO4AQ, the magnesium will replace the zinc, and magnesium is also a 2+ ion, so the formula of the magnesium sulfate would look very similar, MgSO4. That would be our new solution, and the zinc that has been displaced would then form as a solid. Now, the reason why this might be useful is because when we're dealing with ionic equations, we are only including the ions that are involved in the reaction. So the magnesium displaces the zinc, the sulfate ion has absolutely no part to play in that. So if I was to think about it using some of my coloured pens, if the yellow was the magnesium and the green was the zinc and the black is the sulfate, what is happening is the magnesium is going to come in, take the place of the zinc, but the sulfate ion is spectating. That's the proper chemistry term for that. It's not getting involved, it's not doing anything. If it was something other than sulfate, the reaction would still proceed, the magnesium would still displace the zinc. Now, the reason why I'm telling you this is because in our ionic equations, we remove the ions that are spectating. So the sulfate ions are the ones spectating. So what we would then look to do is rewrite this equation just without those sulfate ions being in the equation. So that's not going to change the magnesium. But instead of writing zinc sulfate like this, the reason why they've done it in the question as Zn2+, is because the zinc ions have a 2+ charge, and they've removed the sulfate ions because they are spectating. So those have gone. They need to therefore also not be present on the product side. So when the magnesium becomes magnesium sulfate, the magnesium will now exist as ions, again with a 2+ charge. The sulfate ions, we're getting rid of those because they're our spectator ions. And then the zinc will still form as a solid as it is displaced. So that is your ionic equation. And anytime you're asked for an ionic equation, you remove any ions that are not involved, any spectator ions, they need to be removed. And it might be that you find writing out the full equation, figuring out the ions that are spectating, then removing them is the best way to do this. Now, this is then also really helpful in the next part of this question. Explain why the reaction between magnesium atoms and zinc ions is both oxidation and reduction. Now, there are quite a few ways of thinking about oxidation and reduction. The way that is going to be useful to us here is to think about the mnemonic oil rig, where oxidation is loss and reduction is gain of electrons. So what we then need to think about is the magnesium is becoming, or the magnesium atoms rather, are becoming magnesium ions. How do they do that? Do they do that by gaining electrons? Do they do that by losing electrons? Now, magnesium's in group 2, so it's going to do that by losing its 2 outer shell electrons. And you don't have to write a half equation to answer this question, but that therefore clearly shows that this is oxidation. So the magnesium atoms undergo oxidation, and therefore the other substance has to undergo reduction, because you can't have something losing electrons without there being something there to gain them. So the other sort of half equation that you may look to write, if it's helpful, is the zinc ions becoming zinc solid. And again, what we've then got to think about is how do those zinc ions turn back into atoms, and they're going to have to gain 2 electrons in order to do that. And that is therefore reduction. So to explain why the reaction involves both oxidation and reduction, we're going to need to say something like the magnesium atoms lose 2 electrons and are oxidized, whilst the Zn2+ ions, the zinc ions, gain 2 electrons and are reduced. So there wasn't necessarily a need to write the half equations out, but if you're ever talking about electrons being lost or gained, I would always suggest mentioning exactly how many are lost or how many are gained and being that specific. Again, any questions with that, guys, please let me know. Moving on to question 3, it says explain, so we've got to say why, explain why the reactivity of the halogens decreases going down the group. Now, they've already told us the trend. Sometimes it might say explain the reactivity of the halogens down the group without actually telling you what the trend is. But here, they've told us that they get less reactive as we go down the group. So I guess what we therefore need to think about is what changes as we go down the group. So fluorine is top, then chlorine, then bromine, then iodine, and then there are others, but those are the main 4 that you guys are going to want to be familiar with. So what changes as we go down the group? Well, the atoms get bigger. How do I know that the atoms get bigger? Well, the atomic numbers of these elements increase. So iodine has a lot more protons than any of the others, particularly fluorine, and in atoms there are the same number of protons and electrons. So if iodine has more protons, it also has more electrons than fluorine, and therefore it's going to have more electron shells, and that's going to make it bigger. So every time we go one further down the group, we add another electron shell, which will then have electrons populating it. So as we go down the group, atoms get larger, and that is because there's an increased number of protons and thus electrons as well. So then there are more electron shells. And that, I guess, is the first thing to contemplate. Now, the other thing, when we're thinking about reactivity is always about what's going on with the electrons. Things react to get full outer shells of electrons. So with the halogens being in group 7, so all of these will have 7 electrons in their outer shell, the purpose of them reacting is that they want to gain an electron. So I guess the goal, if you will, is to gain an electron. Why? To fill the outer shell. So then all we've got to think about is, why is it going to be easier for fluorine to gain an electron, and why is it going to be hardest for iodine to gain an electron? And you've basically already answered that by thinking about these things. If fluorine is smaller, the protons are in the nucleus in the middle, and you're trying to gain an electron into a shell that is close to the nucleus, there's going to be a really strong attraction there. But if you're iodine and you're massive and your protons are in the middle and the electron that you're wanting to gain is entering a shell that's really far away from the nucleus, there's not going to be as strong as an attraction. So that's going to be much harder to do. And that is why the reactivity decreases as you go down the group. So key things that we're going to need to mention are basically lots of the things that I've already said here. So atoms get larger as you go down the group. That is certainly one thing that I would mention. I'm trying to think about how to do this because I don't need to rewrite all of this out. So the atoms get larger as you go down the group because there are more electrons and therefore more electron shells. This makes it harder to gain an electron as you go down the group because of the weaker attraction between the nucleus and the electron being gained. So we need to mention somewhere that the goal for the halogens is to gain an electron, and then make reference to the attraction or the ability to pull the electron in for it to be gained. So the bit that I haven't made reference to yet. So further down the group, it is harder to gain an electron because there's a weaker force of attraction between the protons in the nucleus and the electron being gained. Or conversely, if you're thinking about, well, fluorine's the most reactive because it's at the top of the group, it's easier to gain an electron because there's going to be a stronger force of attraction between the protons in the nucleus and the electron being gained. Now, if it asked you to do this for group 1, the trend would be completely the opposite. And that is because the elements in group 1 would like to lose an electron rather than gain one. So if it's easier to gain an electron when an atom is smaller, it should therefore be harder to lose an electron when an atom is smaller. So as you go down group 1, it's easier for those elements to lose an electron because they are larger. So lots of the same thought processes, but this is fundamentally different for group 1, and therefore this is the opposite way round. Okie dokie. Again, any questions, please let me know. Moving on to question number 4, we've got a reaction profile diagram for the reaction between hydrogen and oxygen. So the reaction between hydrogen and oxygen releases energy. A student drew a reaction profile for this reaction, and this is what they drew. The student made 2 errors when drawing the reaction profile. Describe the 2 errors. Now these are higher order questions because rather than them just saying, okay, here's a blank reaction profile, you've got your axes and they're labelled, you draw the reaction profile, you have to, I guess, question what's been done on here. So what you might want to do is just cover that up and think, right, how would I sketch this? What would it look like? Well, if the reaction is releasing energy, the products are going to have less energy than the reactants did in the first place because heat is being lost to the surroundings. That's not what they've got shown here. They've got the products with more energy than the reactants. So that is clearly one of the issues with the students drawing. The other thing that you might get asked to do if you were drawing this from scratch is not only show the level of the reactants compared to the level of the products, but label the overall energy change, which will be the difference in energy between the two, but also the activation energy, which is the minimum energy needed for the reacting particles to collide and collide successfully, which is what leads to a reaction. Now, the activation energy is from the energy that the reactants have to the peak of the curve, which again is wrong. They've done it from the products to the peak of the curve. So they've completely done it backwards. If it was that these were the reactants and we were going this way and these were the products, then it would be okay, but it's not. We're starting with hydrogen and oxygen. So this is one issue, the level of those compared to the level of those, and the other issue is where they've labelled the activation energy. So I guess a couple of things that might be useful here. One, and I know the question isn't asking you to do this, but if I just sketch what the correct version should look like, hopefully that will be useful, and then we can compare mine to that one. And then secondly, we're going to have to think about how we're going to explain what they've done wrong, and I do think this can be quite tricky to word. So from there, And then, as I said, it is always from the bottom of the reactants in terms of their energy to the peak of the curve, which represents the activation energy. And then the difference in energy between the reactants and products is the overall energy change. And because it's exothermic, we should have a decrease in the energy of the products compared to the reactants, because all of this energy is then released to the surroundings. So that would then be your overall energy change. So that's what it should look like. And I think as soon as you read that the reaction releases energy and you therefore know it's exothermic, you might find it useful to just think, okay, I can see they've drawn something. If it's exothermic, what would I expect it to look like? And at least sort of visualize this in your head, or maybe sketch it without all of the annotations, just so that you can then compare. So error number 1, the reactants should have more energy than the products. So the reactants should be higher on the y-axis than the product. And then number 2, I mean, this is kind of consequential on the fact that they've drawn this wrong in the first place, but the activation energy should always be labelled from the energy of the reactants to the peak of the curve. So there we go. Not sure whether having this drawn out first would be helpful for some of you. I definitely think that when you are spotting mistakes in what someone else has done, it is a lot harder than them just asking you to do it yourself, because you'll know how it should be in your head, but the way in which they will draw something, they will purposefully make it wrong in I guess, subtle ways, and you'll be able to convince yourself that actually there's nothing wrong with it and it's all right. So sometimes just thinking it through without looking at this can be useful. But hopefully there's been something for you to have picked up in this video. If you've got any questions about any of the 4 questions I chose, let me know. And if you would like me to do more GCSE questions, again, let me know. And if you've got any specific requests of which questions I do, again, please just let me know. Thank you so much for watching, guys. I hope you're all doing well and enjoying your half term, albeit revising, I'm sure. And I will catch you all soon. Take care.